Hi, and welcome to our MIT808 project where we try to locate the habitat for endangered Cape Parrots.
In terms of our agenda today, we'll give a brief background and the problem statement for our project. We'll talk you through some of the challenges that we faced through this project, the exploratory data analysis and feature extraction we did, our methodology results, and finally the web application we deployed.
Just a bit of background to our project. The Cape Parrot is unique to South Africa, but it's critically endangered with less than 1,000 birds remaining. The survival relies on yellowwood trees, which is critical to their habitat. To support conservation, monitoring forest conditions is crucial, but there's a lack of data which hampers efforts. By using drone-derived RGB imagery, we can automate the detection of yellowwood trees, which reduces the cost of traditional field-based methods and enhances conservation planning for the Cape Parrot. In terms of the data that we had, in each of the 4 forests, we had RGB JPEG imagery. We also had OrthoPhotos of each forest accompanied with a digital elevation model. And we also had LAS point clouds, which are quite large in size. One of the OrthoPhotos is seen here on the right side with its ground truth points label. Some of the challenges of our data is that the forest is quite dense. And once you zoom in, the quality deteriorates. So it's difficult to extract features to distinguish between yellowwood and non-yellowwood trees.
To feature extraction. As the data quality was not good enough to extract features for yellowwood trees, we decided to use statistics of each RGB band to see if color intensity of yellowwood trees distinctly differ from non-yellowwood trees. Before testing the hypothesis, we conducted a thorough inspection of the data available to us. We have data for 4 Southern Mistbelt forests located in the Eastern Cape. Between these 4 locations, we have 399 ground truth points. During the EDA, we discovered that yellowwood trees have very little distinguishable features. However, 2 features really stood out. Yellowwood trees tend to grow in rows, and this is present in 3 of the 4 forests. However, it is unclear whether the pattern stems from human interventions. Also, the second feature indicated that these trees grow at either very high altitudes or very low altitude. We then started extracting the RGB intensity values for each ground truth point. This is split into 3 methods. We first created buffer layers around each point using QGIS. This allowed us to move the ground truth point marking to fit on top of what we believed the yellowwood tree would be. We extracted the mean, median, and standard deviation of the yellowwood RGB intensity. Secondly, we extracted the RGB intensity values of the single pixel labeled as a ground truth point using Rasterio. Thirdly, we repeated the first approach using buffer layers to get a holistic view of the RGB intensity using Rasterio. We also created random points representing non-yellowwood trees throughout each OrthoPhoto to compare the RGB statistics of yellowwood trees to non-yellowwood trees. Lastly, given the importance of altitude, we used the DEM files to extract the altitude of each tree, ground truth points, and random trees in approach 2 and 3. Given our small data set, we decided to train a logistic regression classification model on the color intensity of yellowwood trees and non-yellowwood trees. We fit the model to all 3 data sets, which included the QGIS statistics, the single pixel and multi-pixel statistics. In all 3 experiments, we split the data on an 80-20 ratio for testing and training. For the first model, the QGIS-dependent logistic regression, we imported each OrthoPhoto in QGIS and the ground truth points. We manually created random non-yellowwood points throughout the image and then added a buffer layer around each point to compute the mean, median, and standard deviation of the RGB intensity. During the manual point creation, we tried to ensure minimal overlap between trees. We then fit the logistic regression classification model on the extracted statistics. The second model included the single pixel logistic regression, where we imported the OrthoPhoto directly into Python. We extracted the RGB intensity values for each ground truth point and random point. We trained a logistic regression on the data set. The features included the red, green, and blue band values for each marked pixel, as well as the average of the 3 values, the altitude of each tree, and the interaction of altitude with the average color intensity. The last model was the multi-pixel logistic regression, where we repeated the same process as for the single pixel model. However, we extracted the RGB intensity for the surrounding 500 pixels. We then created a mean value of the red, blue, and green value in the buffer layer. All the other features remained the same as in the second model.
In terms of our results for the model where the statistics were generated in QGIS, we have the best accuracy, which was 83% overall. In our specific project, we are more interested in the accuracy of actually identifying yellowwoods as opposed to the accuracy of identifying non-yellowwood trees. Our precision recall for class 0 was slightly higher than for class 1, but the difference was minimal. For class 1, the precision was 78%, which means out of all instances predicted as yellowwood trees, 78% were actually yellowwood. This is a moderate rate of false positives. In terms of recall for class 1, the percentage was 75%, which means out of the actual yellowwood trees, the model correctly identified 75% of them and just missed 25%. So there's a moderate rate of false negatives.
The single pixel logistic regression model had an overall accuracy of 74.36%. This model included the altitude. The recall is higher for class 0, which was 83% compared to class 1, which was 56%. Therefore, the model is better at identifying non-yellowwood trees than yellowwood trees. Similarly, the multi-pixel logistic regression model had an overall accuracy of 74.4%. The model also includes the average and standard deviation RGB intensity values and the altitude. The recall is significantly higher for class 0 at 89% compared to class 1 at 56%. However, it must be noted that not all yellowwood trees were labeled in the initial fieldwork, so it is possible that some of the false positives actually represents yellowwood trees. More so, the yellowwood tree coordinates can be off by 4 meters, impacting the model's performance of the single pixel and multi-pixel logistic regressions.
Lastly is our web application. We required a way to visualize the models that we developed, so we used Python's Streamlit library to develop the web application. Here are some snippets of the web application. So it allows the user to input the number of random points to generate, and they can also then upload a GeoTIFF image. As we see on the right, random points will then be generated, and it will also calculate the statistics around these random points. After that, it will then make predictions over whether each point is a yellowwood tree or not based on its statistical profile. And we can see the visualization of this, where the yellowwood trees in yellow and the non-yellowwood trees in red. The user can then export these predictions, and it will export to Excel with the latitude and longitude as well as the predicted output.